What are the key assumptions in statistical thermodynamics? Have you ever wondered how the tiny particles in a material can influence its overall behavior? The fascinating field of statistical thermodynamics connects the microscopic world of individual particles to the macroscopic properties we can observe. To understand this connection, several key assumptions are made. Let's break them down in a straightforward way. First, there is the idea of equal probability of accessible microstates. In an isolated system at thermal equilibrium, every possible arrangement of particles that fits the system's energy and constraints is equally likely. This means that no specific arrangement is favored over another if they share the same energy. Next, we consider the large number of particles and states. Statistical thermodynamics works best when dealing with a vast number of particles. This allows scientists to use statistical methods to describe average properties instead of tracking each particle individually. Then, we have the ergodic hypothesis. This assumption suggests that over time, a system will explore all its accessible microstates in a sufficiently random manner. This means that time averages of properties will match ensemble averages across all microstates, making it possible to use statistical averages for physical observables. Another important assumption is weak coupling and energy exchange. When looking at subsystems, it is assumed that they are weakly coupled. This means that energy exchange between them happens slowly compared to how quickly energy redistributes within each subsystem. This allows us to treat these subsystems as nearly independent while still allowing for energy exchange. Thermal equilibrium is another key assumption. A system in thermal equilibrium has stable macroscopic properties over time, with a well-defined and uniform temperature throughout. Additionally, we have the conservation of energy and other quantities. The total energy of an isolated system remains fixed, along with other conserved quantities like particle number. Only those microstates that align with these conserved values are considered accessible. Finally, statistical thermodynamics uses ensembles, which are large collections of hypothetical copies of the system under specific conditions. For example, the canonical ensemble assumes the system can exchange energy with a reservoir at a fixed temperature. These assumptions allow scientists to derive macroscopic properties such as temperature, pressure, and entropy from the microscopic behaviors of particles and their interactions. For instance, the concept of entropy is linked to the number of accessible microstates, providing a way to understand disorder or randomness on a microscopic level. In practical terms, these assumptions help scientists and engineers predict how materials behave, how chemical reactions occur, and how energy transfers happen. By focusing on the statistical behavior of atoms and molecules, we can gain a clearer picture of the physical world without needing to track every single particle.